तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
To a unit impulse will give all the information that is needed for us to find out the response to any arbitrary input. Let us see how we go about it. This is a linear time invariant continuous time system represented as a box like this. Suppose the input is delta t, a unit impulse at the origin, and let the corresponding response h of t is given like this. We also assume in this discussion that if this is a network, it has no initial conditions on the capacitors and inductors, or in other words, in a system, zero initial storage, zero initial stored energy. The reason is we are going to apply the principle of superposition, and whenever number of excitations are present simultaneously, the responses could be superposed only if the system does not have any initial stored energy, otherwise the superposition principle is violated. Okay. Now any arbitrary x of t given as an input something like this, this is a general input can always be thought of. Suppose you take a small narrow section of width delta tau, and then let this at the center we will call that tau I, this point tau I, and this section of the input, a narrow section of time, this area can be replaced by an equivalent impulse. So if you regard this impulse, the impulse will have essentially the same area as this narrow strip, and the area of the narrow strip will be x of tau I times delta tau. So this will be x tau I delta tau, that is the magnitude of the impulse, and that impulse is situated at t equals tau I. So provided you make this slices thinner and thinner, then the approximation will be so much more accurate. So xt can be regarded as, approximated as, number of impulses. A particular impulse which we have sketched in the figure is x tau I delta tau, that is the area under the curve, that is the magnitude of the impulse, and that impulse is situated at tau I. So this is the impulse that we are talking about. This section of the input is replaced by an impulse, and several such impulses starting from for the whole duration of the time will be approximately equal to x of t. So x of t can be regarded as summation of several impulses. So that means your x of t is now being regarded as several impulses like this. So if we want to find out the response to this arbitrary input, we can find out the response due to the individual impulses and add them up, that will be your total response. And in the limit as delta tau goes to 0, then the response will be faithfully the one that will be obtained when the actual x of t is present. That is the philosophy, that is the strategy that we will adopt. Because we know the impulse response, an impulse at the origin gives rise to h of t. So any impulse displaced by some amount will also give rise to an impulse response which is displaced by the same amount, translated by the same amount. And by additivity property, if unit impulse gives h of t, an impulse of this magnitude will be this times that h of t. So that is the principle that we are going to adopt. So now we now say delta t gives rise to a response h of t. Therefore, any impulse which is displaced by a certain time interval will give rise to h of t minus tau I. What is the principle which sanctions this? This is a time invariant property. Because the network is time invariant, any shift in the input will correspond to the corresponding shift in the response. That is what we had discussed earlier. And instead of an impulse of unit magnitude, suppose you have x tau I delta tau, that is the magnitude of the impulse, delta t minus tau I. If that is the input, you get correspondingly x tau I delta tau h of t minus tau I. So a shifted impulse will give rise to a shifted impulse response, and impulse magnitude increased by this amount will also give rise to a response which is increased by the same amount. And now here we have a summation of all such things, x tau I delta tau delta t minus tau I, summation as limit delta tau goes to 0, that is your x of t, and that must correspondingly give me limit as delta tau goes to 0 of x tau I delta tau h of t minus tau I, not one such set of responses, number of such responses summed on various ti's, or I will put I summed on various i's. So in the limit, this entire thing goes to x of t. So as you make delta t goes to 0, all these impulses is equivalent to the input xt as we have seen. From xt we have generated these impulses. You make them closer and closer, approximately that will be the same as your x of t. So x of t is regarded as a series of impulses, and correspondingly this will now be, you have a number of these things where delta t, so it is an integration of x tau h t minus tau. So tau I is not discrete points, it continuously it exists, delta t d tau, that is your y of t. So y of t is obtained as x tau h t minus tau d tau. That is how we can obtain in the limit the output y t corresponding to this x of t. And in general, the most general case, this integration must last from minus infinity to plus infinity, but in the more usual cases the limits can be further restricted, as we will see at a later point of time. So in other words, given any input xt, the output can be obtained as x tau h t minus tau integrated between minus infinity to plus infinity. This is a function of time. Tau is the variable of integration that gets cancelled out. Final result will be a function of time. So this t stays, and that is your y of t. And this particular type of formulation is usually represented as ht xt star ht. This is referred to as convolution integral. So if you convolve two functions of time xt and h of t, the meaning is this particular integration, x tau h t minus tau d tau. So let me rewrite this. We will come back to the impulse response and the calculation of y of t, but let us spend a few minutes on the meaning of convolution integral. So convolution integral of two quantities f t, convolution of f t and g t represented in this manner is f of tau g of t minus tau d tau. This is a symmetrical arrangement. We can also write this as g tau f of t minus tau d tau. As I said, normally the integration is minus infinity to plus infinity. This is called the convolution integral, sometimes called Faltung integral. That is, the German name is Faltung integral. So what is involved in this integration? It is instructive to see physically how we interpret this integration, this convolution principle. So let me illustrate this by means of this picture here. You have two time functions f of t and g of t. You would like to find the convolution of these two. What you do is you keep one of these f t fixed. So, let us say this is f t, this is fixed, and this g of t, suppose you reverse this, the time axis. That means g of t is like this. This what you are having here is g of minus t. This is g of minus t. That means you fold it. G of t is folded along the y axis. So, the sequence of values which it takes for positive t will now take for negative t and vice versa. So, you fold it along the y axis. This is g of minus t. And then suppose you want to find out the convolution integral for a particular value, say t1. Then this g of minus t, you advance it in the forward direction by an amount equal to t1. That means this is g of minus t. You advance it by an amount t1. This becomes g of minus of t minus t1, that is g of t1 minus t. That means you shift it, that you are having this. Now, we have the product of, in this convolution here, f tau g t minus tau. Therefore, what you are doing now is this original f of x that you are having, or f of tau that you are having, and this shifted g of t, you multiply them out, and this will be your result. The product of these two functions will be this, and you take the area under that curve, that is the integration, that will give the convolution value at t equals t1. In other words, what we are doing is you take original one time function, keep one time function as it is, the other time function you fold it, then shift it by the required amount, then multiply, then take the area under the curve, that is integrate. So, the key words are fold, shift, multiply and integrate. These are the four words, the key words that are involved here. This will be explained a little clearly, more clearly perhaps, by taking this particular thing. Suppose this is f of t and then you are having a g of t here. This is g of t is the triangular curve. So, what we are doing now is, instead of having like this g of t, you shift it, you fold it like this. So, g of t originally was like this, now you folded it, that means you made this run backwards. This is now g of minus t. Now, depending upon the point where you want to find the convolution, you shift it like this. So, for various shifts you find out the product of these two curves and find out the area under that curve, and this is how one can calculate the convolution values, integral values for elementary time products. So, the key words here are fold, shift, multiply and integrate. So, you are having here f, g of t is the time function, g of minus t is what is obtained by folding, shift it. So, g of t minus tau, you shift it by the amount at which you want to calculate the integral. At t equals t1, if it is you want to find out the product of this at t1, you fold it, you shift it by that amount t1. In a general t, g of t minus t1. Multiply. So, f tau is multiplied by g of t minus tau. And then integrate, that means you find out the area under this curve. So, these are the steps that are involved. If you keep this at the back of your mind, we can find out the convolution of simple functions quite easily without going to the mathematics. From physical graphical approach, you can find out the convolution of different functions very easily. Now, let us look at these limits. This is the general expression for the response yt for any given x tau, any given x t. So, however, when we talk about causal systems, special case of causal systems and causal signals or causal inputs. If we take that, then what are the consequences? If the system is causal, then an impulse x delta tau given here cannot have an impulse response for negative values of time. That means ht will be 0 for t less than 0. So, if the system is causal, the impulse response must be 0 for negative values of time. So, the consequence of this causal system is ht is 0 for t less than 0. If the input is a causal input, that means xt is 0 for t less than 0. Because of these two restrictions, this impulse, this convolution integral that we are having here minus infinity to plus infinity, these limits can be now be simplified, because x tau is going to be 0 for negative values of tau. We need not start the integration from minus infinity, you can start from 0, right. Similarly, tau is a running variable. When tau exceeds t, then this h of t minus tau, the argument becomes negative, therefore that is going to be 0. Therefore this integration need to be carried out only for up to tau equals t instead of infinity. So these lower limit and the upper limit can be reduced now to 0 and t. Then we can write x tau h of t minus tau d2. So for the special case of a causal system with a causal input, we need to carry out this integration only between the limits 0 and t, not between minus infinity to plus infinity. In particular, if x t for example may have an impulse at the origin, so we must take that effect of the impulse into account. Therefore it would be advisable for us to start the integration from 0 minus, so that that impulse is fully taken into account in our calculation. Similarly, the impulse response may have an impulse at the origin. It may be possible that if you give an impulse, then there may be impulse present in the response also. That means h of 0 may also have an impulse. Therefore to take that into account, you can take this to plus. So 0 minus and t plus are taken to account for impulses at the origin in xt on one hand and ht on the other. If you have no such impulses, then you can always take the 0 and t. But if you have impulses present, it is advisable to take from 0 minus to t plus. That is how it goes. So to summarize this discussion up to this point is, given the response of a linear time invariant continuous system to an impulse, we describe this h of t. H of t is called the impulse response. This gives complete information about the system to enable us to calculate the response to any input. And so any given input xt can be regarded as a summation of several impulses, as we have taken like this, and each impulse gives rise to a corresponding response which can be calculated in terms of the impulse response. Putting all of them together, we come to an integration. Y of t is given by this integral, which is called the convolution integral, and the meaning of convolution we have seen. And in particular, when we are talking about causal systems with causal inputs, the limits need not be from minus infinity to plus infinity as it would be in a general case, but in the particular case of these type systems between 0 to t, in particular we may have impulses at the origin both in h of t and x of t. To take care of them, you must take the integration from 0 minus to t plus, otherwise only half the impulse will be taken into account. Now let us work out a few examples to illustrate these ideas. Let us take an example to illustrate the idea of convolution. Let us take a general function f of t, try to convolve with delta t and see what happens. So you have two time functions, and since the final convolution is a function of time and you are doing some integration, it would be advisable for us to involve another variable, a dummy variable, which gets integrated in the process. So let me say that this is tau and this is f of tau, f of tau. Now delta tau is this. So delta minus tau is also the same thing because it is an even function. So if you fold it, it becomes the same thing, delta tau. So that means delta tau is now here, delta minus tau, and in order to, what is it that we want to do? We want to take f tau delta t minus tau d tau, and you want to integrate that. So instead of delta tau you must take delta t minus tau, that means this you must take delta minus of t minus tau minus t. That means you must advance this delta by an amount equal to t. So if you want to calculate the product the convolution at a value t, you shift it by an amount. So this will be delta t minus tau, where this is the value t. So this shift depends upon the particular value t which you want at which you want to evaluate. For 1 second you shift it by 1 second, if you want to evaluate at 2 seconds you shift it by 2 seconds, and so on and so forth. Now you have folded this signal, then shifted this signal, then multiply these two out. If you multiply these two out, you have f tau multiplied by delta t minus tau. What you get is, because delta is 0 everywhere else except at this point, you have a small delta here whose value is f at the value t delta t minus tau. And when you integrate that, f tau delta t minus tau, that will be equal to the area under this curve is f of t. So the result is that f t convolved with delta t is f t itself. Answer is f of t itself. This is a very interesting result, that the delta function when it is convolved with any time function yields the same time function identically without any change. It is something like what you may, of course you may not have delta in practice, but if you have a narrow slit, for example instead of a delta function, suppose you are having a small slit like this and you do the same convolution, then you get an output which is very closely resembling this f of t. Something like you are, for example, the soundtrack on a film passing through a sensing head, or a sound signal on a tape passing through a head. Then if you have a narrow slit, when you pass it through this, and if a response is something like similar to the product and then integration over that small area, then you get more or less essentially the same signal as the output, something similar to that. Now let us take a second example. Let us see what happens when a step function is convolved with another step function, u of t convolved with u of t. So the result is, suppose the result of this is called g of t. According to the formula, this will be u tau, u of t minus tau, that is the second signal, d tau, and you integrate that over the limits which are appropriate to this. Let us see what they are. Now you take first of all u tau, this is u tau, this is 0 here and this is equal to 1. Now u of minus, to take care to picturize this, u of tau is like this, u of minus tau will be something like this. This is u of minus tau. But then you do not want u of minus tau, you must shift it by an amount equal to t. U of t minus tau would be something like this. That will be u of t minus tau, where this amount is equal to t. So you multiply these two, this is also equal to 1, this is multiplied by this, you will get this curve 0 to t. So the area under this curve, after all when you want to integrate this, it means you are finding out the area under this curve. The area under this curve is t. P units. Therefore the result of ut star with ut, or the convolution of that, is going to be t for positive t. So we can say this is t for t greater than 0, because we have shifted in the forward direction. Now let us imagine what happens for negative t. This is for t, what you have pictured here is for t greater than 0. What happens when t is less than 0? So this is u tau, this is u of minus tau. For negative t, you shift it in the other direction. Therefore you have a curve like this, that will be ut minus tau for t less than 0. So when you make the product of these two curves, it will be 0, because when this is non-zero the other is 0, when this is non-zero this function is 0, therefore the product is 0. Product of u tau times ut minus tau is going to be 0 identically, therefore area is going to be 0, therefore the convolution product is 0 for t less than 0. So the product is described by r of t, that is a ramp function. That means ut star, it will be like this. If it is 1, this is 1. So the conclusion is ut convolved with ut equals r of t. So the idea of convolution is relatively easily seen in simple cases by plotting these graphs in this manner. Again the key words are fold, shift, multiply and integrate. Integrate means finding out the area under the curve. For simple geometries the area under the curve can be easily found out without doing integration, and you can picture what is the final result is going to be using these concepts. Now one more example. Given h of t for a type of system that we are talking about is 2e to the power of minus t minus e to the power of minus t ut for an initially relaxed linear time invariant continuous time system, find response to a ut b e to the power of minus 3t ut. So that means we are asked to find out using this impulse response the response to two arbitrary inputs. Now let us see the first one. If u of t gives rise to a response at, then at can be found out by convolving u of t with the h of t. So I will write this as the input now is ut and that is convolved with the impulse response ht. So the meaning of this would be both are now this is a causal system, the impulse response is 0 for negative values of time, and the input is also causal, therefore we can straight away say this is 0 to t ut. So I will call it u tau ht minus tau d tau, right. Then this can be regarded as 0 to t. In the interval 0 to t, when tau takes from positive values, this is going to be 1 anyway, therefore we can disregard this. So h we can write this 2e minus of t minus tau minus e of minus of t minus tau d tau. Again u tau is there, u of t minus tau is there, u of t minus tau is going to be 1 in the interval from 0 to t, because as long as tau is less than t, then t minus tau is going to be positive, therefore both this u tau here and u of t minus tau that is coming here are going to be 1 in the range of integration, therefore they can be omitted. So this will be what you are having here, and this can be written as you in the integration e to the power of minus t comes out for the first term, therefore you have 2e to the power of minus t, and then when you integrating of e to the power of I'm sorry there is some mistake here, I should have put this minus 2t, kindly note this, therefore this is minus of 2 of t minus tau, otherwise there is no meaning in writing two things, 2 minus t minus tau, therefore you have e to the power 2e to the power of minus two t and 0 to t e to the power of tau d tau, that is one term, and then minus e to the power of minus t, that is a common factor that comes out, e to the power of tau d tau 0 to t. you can carry out these two integrations and final result will be e to the power of minus t and minus e to the power of minus 2t. This is valid for t greater than 0. So the a of t is now obtained as, answer is e to the power of minus t minus e to the power of minus gt. That is the answer as far as the first part is concerned. Yeah. The second part, the yt is now 0 to t again, u tau, not u tau, this time is e to the power of minus 3 tau, that is the input. This is going to be 1 for the range of integration. Ht minus tau, that is 2 e to the power of minus 2 t minus tau minus e to the power of minus t minus tau d tau. That is the integration that is to be done, and working out as before, this is the integration with reference to tau, therefore e to the power of minus 2t can be brought outside, 2e to the power of minus 2t, then 0 to t, e to the power of minus 3 tau and e to the power of minus plus 2 tau, we have got e to the power of minus tau d tau. And then for the second part, you have e to the power of minus t that can be pulled outside, and the integral from 0 to t, e to the power of minus 3 tau and e to the power of plus tau, therefore e to the power of minus 2 tau d tau is what we are getting. And if you carry out this work, the answer will be finally minus 3 upon 2 e to the power of minus 3t plus 2e to the power of minus 2t minus e to the power of minus t upon 2 for t greater than 0. Of course, for t less than 0 it is going to be 0. Notice that in this particular case we have found out the complete solution. After all, the input now e to the power of minus 3t, that means the forced part of the response will have only this particular complex frequency which is equal to minus 3. So this is the forced part of the response. This is the response which you would have obtained by taking the particular integral solution of the differential equation. And this part is the natural response which contains the response when there is no particular inputs, no sustained inputs. Actually, as a matter of fact, as you can see, the impulse response, what do you mean by impulse response? An impulse appears at t equals 0 and afterwards there is no input. That means whatever follows is kind of natural response of the system. Therefore, the impulse response here, whatever frequencies are present here are the natural frequencies of the system. And the forced response will, for e to the power of minus 3t, will have also e to the power of minus 3t. So that you can recognize this to be the forced response of the particular integral solution, and this is the natural response or what comes from the complementary solution of the differential equation. So at this stage, let us summarize what we have done so far in the question of introductory system concepts. We have seen how systems can be analyzed, particularly transient behavior of systems. We have looked at various methods, the classical differential equation approach, which entails a lot of involved calculations to find out both the complementary function as well as the particular integral solution, and even more so finding out the initial conditions in a differential equation of a large order. Then we said equivalent information of the differential equation can be obtained through the system function concept h of s or to the frequency response function h of j omega. We will exploit these two particular functions in when we are discussing the Laplace transformation and Fourier transform techniques at a later point of time. We also said that equivalent information can be provided by the impulse response method, impulse response h of t or the step response a of t. We have looked at some detail only the impulse response as far as our previous discussion goes. A similar analysis can be given in terms of the step response as well. Step response is called a of t, as we have mentioned here. Almost identically we can carry out the analysis. We have also some kind of convolution integral involved there also, but we will do this later after we study Laplace transformation methods. So impulse response and step response also can be used to characterize the linear system, and here again we are calculating all this in time domain only. So these are all different ways of describing the input output relations of a linear system. the differential equation approach, the system function approach, both as a function of s, both as a function of j omega, or in time domain using either the impulse response or the step response, sometimes called indicial response. The step response is also called indicial response. Some of these techniques we will return to later when we are talking about Laplace transformation techniques. And so we will close our discussion of the introductory system concept at this stage. Let me now give a set of examples for you to work out as in the form of an exercise. First question in the exercise is, classify the systems given by the following equations as linear or nonlinear, time variable or time invariant, continuous time or discrete time. So the equations are A, t squared plus 1 dy by dt plus 2ty equals x. B, yn equals cos n omega xn. C, yn plus 1 plus y squared n equals 2xn plus 1 minus xn. D, 2d squared by dt squared plus 2y dy dt plus 4y equals 2 dx dt plus x, whereas usual notation x is represents the input and y the output. So this is the first question. Second question will give you a series of functions of time 1, 2, this is 10, this is f1t, x axis is always time, f2 1, 0, minus 4, and this is 0 from, this is f2. f3 1, 2, like this is minus 3 and here is minus 4, everywhere else is 0. This is f3. f4 1, this is 2, comes down, this is 3, this is 3.5, and the value here is 2, the value is minus 3. So 4 functions of time are given to you. The x-axis is always in seconds, function of time, and f1 to f4, you express f1 to f4 in terms of singularity functions. So in terms of step functions, ramp functions, etc., you express this, find out expressions for this in terms of step functions and ramp functions, that is the singularity functions. That is the second problem. As a third example, let us take this circuit where a source Vs of unknown waveform is driving a circuit containing an inductor, a resistance, and a capacitor. Values are given. If the Vc has got this particular variation, the waveform of Vc is given, find Vs of t and express this in terms of singularity functions and sketch its waveform Vs of t in this given this circuit and this waveform of Vct. This is part A. Do a similar analysis for this circuit in which again the value of the voltage Vc is given by means of this particular variation, 4 volts to minus 4 volts, it decreases from 0 to 16 seconds and remains 0 for further values, other values of time. And if this is the value of Vc, find out the expression for Vs of t in terms of singularity functions once again and sketch the form of Vs in terms of using impulses, ramp functions, and step functions. So this is one problem which is an exercise on using the singularity functions. Okay, so this is these are two circuits which you can analyze using the concept of singularity functions. The fourth problem, we have, let us take a circuit in which a switch is closed t equals 0, 1 ohm, 2 henries, 1 ohm and 2 farads. Call this I1 loop current, call this loop current I2. So this is a exercise in differential equations. So write down the loop equations, write the loop differential equations in terms of I1 and I2 and in terms of differential operator D. B, taking I2 as the output and Bs as the input, write the differential equation relating the two. So you have a second order differential equation relating I2 as the output quantity y and Bs as the input quantity x. See, if Vs of t equals 33 cos t, find I2 0 plus and I2 prime 0 plus the initial value of the second current and its derivative, assuming 0 initial conditions at t equals 0 minus in the inductor and capacitance, assuming that inductor and capacitance are initially uncharged. 1 minute. 0 initial current, no, we will put this assuming that, assuming 0 current at t equals 0 minus in the inductor and the capacitor voltage Vc at 0 minus is 5 volts. And using this information, initial conditions, D, find I2t for t greater than 0. So that means this is an exercise in the use of a differential equation approach. You have to find the initial conditions and finally find the total solution for I2 of t. Fifth problem, 12 volts. The switch is opened at t equals 0 after a long time, and you have a circuit in which you have two inductors. This is 2 henries, 4 ohms. This is 4 henries, 4 ohms. This is 1 ohm, I1 and I2. The switch is kept closed for a long time, so inductors have some currents established in them, and once the switch is opened, find I1 0 plus and I2 0 plus. This is an illustration of the situations where inductor currents can be discontinuous. So using the principles that we have talked about, find out I1 0 plus and I2 0 plus. Assume that initial conditions have been reached prior to the closure of this. Well, when the switch is closed, steady state conditions have been reached, and therefore the inductors carry some current. Once it is opened out, find out the new currents. 6. The system function h of s is given by 2s plus 1 divided by s squared plus s plus 1 for a single input, single output, linear time invariant system. It is a linear time invariant system, single input, single output system is this. Find the complex frequencies in the natural response of the system. Find the complex frequencies in the natural response of the system. Of the system. B. Find the forced response to an input e to the power of minus 2t. If the input is e to the power of minus 2t, what is the forced response of the system? That is 6. 7th problem. We have two functions of time, ft 0 to 2 seconds, which has a value of 1, and g of t, which is a triangular pulse 0 to 1, this is 1, that is g of t. These are the two functions f t and g t that are given to you. Sketch A. F t convolved with g of t, the convolution of f t and g t. B. F of t convolved with itself. So it would be advisable for you to work this out graphically. You can verify them by through analytical working, but a graphical procedure is more illustrative. The last problem, the impulse response of an initially relaxed, that means there is no initial stored energy, linear constant parameter network is 4 e to the power of minus 2t ut. That means this is h of t. Find the response of the network, of the same network find the response of the same network to A, an input ut, that means find the step response. B, an input e to the power of minus t ut. That is, taking this as h of t, use the convolutional principle, find the response to input of u of t, that is step response, and find the response to a general input e minus t ut, assuming once again that the network is initially relaxed.